Today, we're talking about the cosmic recipe for gold. We're going to trace its journey, all the way from, say, a wedding ring on your finger, right back to some of the most extreme events you can possibly imagine in the universe. So let's dive in.
So have you ever looked at a piece of jewelry, or even just the electronics in your phone, and wondered, where did that gold or that platinum actually come from? It sounds like a pretty simple question, right? But the answer is, well, it's incredibly complex. For decades, scientists have been on this cosmic hunt, trying to figure out where the heaviest elements get made. And honestly, the clues they've found have been all over the place and kind of confusing.
Okay, so to really get to the bottom of this mystery, we first need to understand the basics. The fundamental cosmic recipe for how stuff gets made.
See, your everyday star, it's like a factory that's really good at making the basics. It can fuse light elements, hydrogen into helium, carbon, oxygen, that kind of stuff. But when you want to make the real heavyweights, we're talking gold, platinum, uranium, a regular star's core just doesn't have the oomph. It's not hot enough, not dense enough. For those, you need something way, way more extreme.
And that something more extreme has a name. It's called the R process. That R stands for rapid, as in rapid neutron capture. And it's exactly what it sounds like. Just picture an atomic nucleus getting absolutely hammered, just bombarded with neutrons, so fast and furiously that it doesn't even have a chance to fall apart. It just gets bigger and bigger and bigger, building up all these super heavy elements in, like, the blink of a cosmic eye.
And here's where things got really interesting. When astronomers started looking around, comparing our sun to other stars, they noticed something weird. The relative amounts of all these heavy R process elements, they were the same, like everywhere. It's like finding out that every single bakery on the planet uses the exact same recipe for chocolate cake, down to the gram. This idea got a name, universality.
So this incredible consistency pointed to one conclusion. There must be one single, really reliable cosmic event out there that's cooking up all these heavy elements and sprinkling them across the galaxy. The recipe seemed to be universal. Case closed, right? Well, not quite. Because as astronomers started looking closer, especially at some of the oldest, most ancient stars in the universe, they found some rebels. Yeah, these ancient stars, these relics from the dawn of the universe, they just weren't playing by the rules. They didn't follow the recipe at all. Their chemical makeup was just plain weird.
And take a look at this, because it really shows you the problem. See those black dots? That's our standard universal pattern. But now, look at the red and pink triangles. See what happens? Right around element 55, they just nosedive. The amounts just plummet. They're missing a huge chunk of the heaviest elements. This isn't just a cake that's a little off. This is a cake that's missing, like, all the flour.
And the strange thing is, the weirdness went in both directions. So some stars had that massive drop-off we just saw, but others had the complete opposite, something called an actinide boost. That's a huge overabundance of the really, really heavy stuff at the very end of the periodic table. Think thorium, uranium, all that radioactive goodness. So you can see why this was such a headache for astronomers. How could this same process, the raw process, create such completely different outcomes?
So what's the deal? How do you solve this puzzle?
Well, a new theory might just be the answer. It's a way to bring both the rule followers and the rebels under one single, elegant umbrella.
Right, that's the million-dollar question, isn't it? How can one single theory explain both the consistent, almost boring recipe we see everywhere and all these bizarre, wild deviations in the outliers?
Well, the answer might lie in a new model called Heavy Element Freezeout, or HEFO for short. And you're going to love this. The best way to get it is to go back to our baking analogy. Okay, so picture this. Step 1, you've got your ingredients. It's this super hot, super dense soup of protons and neutrons. Step 2, the oven. This is some kind of cosmic explosion where the whole environment just rapidly expands and cools down. Now, here's the crucial part. Step 3, the freeze. As it's cooling, you hit this one critical moment where it's just cool enough that all the nuclear reactions just stop, dead in their tracks. They freeze out. And whatever mix of elements you have at that exact instant, that's it. It's locked in place. It's like pulling the cake out of the oven. That's your final dish.
And this is where the theory gets really, really beautiful. Because what determines that final dish, that final mix of elements, it's not a million different complicated things. It's actually incredibly simple.
It turns out the whole final pattern, the entire cosmic recipe, is basically determined by just 3 key things at that precise moment of freeze-out. What's the temperature?
what's the neutron density, and what's the proton density. That's it. Just those three things.
And here is the big aha moment. That universal pattern we see in most stars, that's what you get when those three conditions, temperature, neutron density, proton density, are just right in one common stable configuration. But what about the weird outliers? Well, you get those just by tweaking the dials on the same three conditions. Turn up the heat a little, add a few more neutrons, and bam, you get a totally different outcome. It's not a different recipe, it's the same recipe. You're just changing the oven temp and cooking time.
And this is the incredible power of the HEFO model. You can see it right here. The scientists who developed this literally showed that by plugging in slightly different values for those three parameters, they could create patterns that perfectly, and I mean perfectly, match the weird data from those rebel stars. The drop-offs, covered. The actinide boosts, covered. It all fits. It's one theory with one set of rules that finally explains the whole shebang. But hold on, because this elegant solution leads to an even bigger, more profound idea, one that could fundamentally change how we think about the very first moments of the universe.
Okay, so for a long time, the main theories for where all this happens, where these cosmic ovens are, were pretty dramatic. Massive exploding stars called supernova, or the insane collision of two neutron stars.
Now, in that standard story, you've got to wait a long time. Millions of years have to pass after the Big Bang before the first stars can even form, and then they have to live their lives and die or merge to create these elements. But think about the conditions we described for the HEFO model, that hot, dense soup of particles. Doesn't that sound an awful lot like the early universe itself, like just seconds or minutes after the Big Bang?
And that's exactly what the authors of this study are proposing. They suggest that tiny, super dense pockets in the brand new universe, little fluctuations in the fabric of space-time itself, could have acted as the perfect little ovens for this HEFO process. And if that's true, it means the heavy elements didn't need to wait for stars at all. They could have been forged right there, in the first few minutes of creation.
And that just leaves us with this absolutely staggering thought. The gold on your finger, the platinum in your phone. What if it's not the recycled ash of long-dead stars? What if it's something much, much older? A direct relic from the dawn of time itself. A primordial artifact with a recipe that was written not millions of years after the Big Bang, but during its very first fiery moments.